Now let us consider the second experiment, transfer and drain characteristics of a MOSFET. So earlier you studied input and output characteristics of a BJT. Now we are learning regarding transfer and drain characteristics of a MOSFET. So if we consider a BJT, in the earlier case we studied BJT, so it was a current controlled device. What you used to do was, so if this was a transistor, so you add three terminals. So one is named as base, other is the collector, and the third terminal is your emitter. So made emitter as common, so it was called as common emitter configuration. So in order to turn on this transistor, what you used to do was, you're trying to provide current, right? You're trying to provide current at this location, that is, you're providing current to the base terminal. So when you provide current to the base terminal, so there was a flow of current from collector to emitter. So the switch would be turned on when we provide sufficient amount of current to base of the transistor. It was in case of BJT. Okay. And now in case of MOSFET, so there will be again three terminals, but now it will be named as gate, drain, and source. So these are the three symbols which you need to remember. So now it is called as what? Gate, drain, and a source. In order to turn on this MOSFET, we need to provide sufficient amount of voltage between gate and the source. It is not current, remember, it's not current, it's the voltage. So if you provide sufficient amount of voltage between gate and source, that is VGS, then the current would flow through this MOSFET. The current which will be flowing through this MOSFET would be ID, which indicates that the MOSFET is conducting. So let us see the exact working of this. So just you remember that there will be three terminals: gate, drain, and source. In order to make the current to flow from drain to source, we need to apply voltage between gate and a source. So now you look over here. So this is your source and this is your drain. So this is the gate. So let us consider we are having an voltage. So here it is showing as a 0. Let us take there is an voltage of around, let's consider there is a voltage of around 5 volts. Okay. Now a drain is containing voltage of 5 volts, and it is, the voltage is stagnant here just because you are not allowing to flow. The flowing of current from drain to source is not allowed. So there exists a voltage of 5 volts. When we apply voltage between source and gate, so this is your source and this is your gate. When you apply this VGS, when you apply voltage between gate and source, what happens is MOSFET starts conducting and current starts to flow from drain to source. Then what happens? This voltage would be dropped and the current starts decreasing. Okay, the amount of current which is allowed to pass from drain to source depends upon the amount of voltage which is given to the gate terminal. You look over here. So we are taking this as VD and we are taking this as ID. ID is the drain current which flows from drain to source. Right now there is no current flowing just because VGS is 0. Now let us give sufficient amount of voltage. Okay, so just look over here. Still it is 0.6 volts. At 0.8 volts, just look over here, the current is flowing. Okay, so the current is flowing. So this is indicated over here. When you apply more voltage, okay, between gate and source, just look over here, 1 volt, so more current is flowing. So this is indicated over here. Let us apply still more voltage. So still more current is flowing here. You just look over here, more current is flowing. If you apply VGS, so about 3.2 volts, so still more current is flowing. You can just look over here, and let us increase it to 5.652. So more current is flowing. You can look over here, more current is flowing. So in order to make the current to flow from drain to source, what we need to apply is the voltage between gate and source. When you apply the voltage between gate and source, it starts conducting and the MOSFET is turned on. If you reduce this voltage, or if you make this as 0, okay, now let us make this as 0, what happens? Automatically it is turned off. There is no flow of current. Okay, so this is the operation of MOSFET. So by applying the voltage to the gate and source, between gate and source, it will be turning on the MOSFET. So just look over here, so it is turned on. Okay, so this is the working of the MOSFET. Now let us come back to the circuit. So now in MOSFET we will be learning the transfer and drain characteristic. Drain characteristic can also be called as output characteristics, whereas this is transfer characteristic. The first thing what we need to do is we need to check what is the aim of the experiment, and the aim of the experiment is to plot the transfer and drain characteristics of the MOSFET. And the apparatus or the components which we require are MOSFET. The name of the MOSFET which we will be using here is IRF7403. This is an N-channel MOSFET. Next, we will be making use of a single resistor. Okay, so this is your MOSFET IRF7403 and a resistor of 560 ohms. We require an ammeter to measure the current, and we require an voltmeter. So there are two voltmeters which is used to measure the voltage. And the next thing is circuit diagram. So this is the circuit diagram to check the transfer and drain characteristic. Now background theory, you already came to know what is meant by MOSFET. It is nothing but metal oxide semiconductor field effect transistor. It has three terminals called drain, source and gate. So in order to turn on the MOSFET, we need to apply sufficient voltage to the gate terminal. Okay, so the characteristics can be of two types. One is the output characteristics or the drain characteristics, or one and the same, and the other is the transfer characteristic. So the next is the procedure. So first we will be studying the procedure for transfer characteristic, and then we will be studying the drain or output characteristic. Before studying the transistor characteristics, we need to make the circuit diagram, right? So we need to make the circuit diagram. So this is the circuit diagram. So in order to rig up the circuit diagram, we will be making use of a multi-sim simulator. Now let us rig up the circuit. So what we require is one MOSFET. So it's a transistor. So go on to a transistor. So this is place transistor. Click on this here in a transistor. So we need to check for MOSFET. So here, so MOSFET. So this is the MOSFET. So this is a 3-terminal MOSFET. So you are not having IRF over here. So click on this one, MOSFET underscore 3-terminal N. So here you just type in IRF 7403. So this is the MOSFET which you will be using. Click on OK. So the MOSFET is ready to be placed over here. Now we close this. Now you have picked the component MOSFET. The next thing is we require a a resistor. Again click on place basic. Here you select a resistor. Next 1K is selected. Click on OK and place the resistor over here. Then close this. So the resistor is placed, but the value of the resistor is 560 ohm. So we need to change it to 560. So double click on this resistor. So here you give the value as 560 and click on OK. So this is 560 ohm. Next we require power source. We require two power sources. So go to place source and click on power source. We require two DC power source. Click on OK. So this is available here. Again they are selected here. You click on OK. So another power source is available. Whenever you place a power source, we need to take one ground for the circuit. So place the ground over here. So right now we have a resistor, a MOSFET and two power supplies. Next what we require is one ammeter and two voltmeters. So go to place indicators, click on that, select ammeter, click on OK and place the ammeter over here. Next select voltmeter, click on voltmeter vertical. So next click on OK. So one voltmeter. Similarly you require other voltmeter. You click on the other voltmeter. So now everything is ready. We just need to connect it using the connecting wires. So you connect this. So the voltage is given to the gate terminal. So the negative is connected to the ground. Then we are connecting a resistor to the drain. So this is your drain. Then that has to be connected. So here this is positive and negative. Here it is positive. So you just flip horizontal so that the positive terminal of ammeter is connected to the positive terminal of the battery. Now we connect this one, and then we connect voltmeter, we connect the voltmeter over here. There is power supply. And next we need to connect the source to the ground. Now you connect this over here. This is your negative. Next we need to connect the other voltmeter. So you connect it here, other terminal to here. So now the circuit is ready. Now we need to name the terminals. We already know that MOSFET will be having three terminals. So this is gate, and this is drain, and this is your source. So the voltage between gate and source can be named as VGS, right? Similarly, the voltage between a drain and the source can be named as VDS. Okay, and this is your ammeter. So the current which is flowing through the ammeter is entering into drain, so we'll be calling this as ID. So we need to name this voltmeter as VGS, this voltmeter as VDS, and this current as ID. So that is what is given: VGS, VDS and ID. And let us name this voltage as V2 and the other end as V1. Let us name this as V2 and name this as V1. So in order to name this as VGS, double click on this, go to labels, name it as VGS. Go to display, uncheck this one, uncheck all the values except show labels and click on OK. This is named as VGS. Now this should be named as VDS. Double click on this, go to label, name the label as VDS, click on the display, uncheck all the attributes except show labels and click on OK. So this is your VDS. Now this should be named as ID, current ID. So click on the label, name this as ID, then click on the display, uncheck this one and uncheck all the attributes and click on OK. So this is your ID. So we'll be naming this as V2 and this as V1. Okay, let us name this label as V2 and the display only for power source, both of them should be visible, that is check, show label and show values. So this is your V2. Now here the same thing, go to labels and name this label as P1 and click on the display, uncheck these two should be checked and click on. So this is your V1. So now the circuit is ready for simulation. Just check over here, everything is ready. Okay, and now what we need to do, we need to check the characteristic. So first we will be checking the transfer characteristic. Okay, so the first step in the transfer characteristic is the same thing as in the first experiment. First you make all the voltages as 0, you make this as 0, again you make this voltage as 0, click on OK and try to run the circuit. So everything is set to 0. Now stop it, and now let us go to the second step. Initially keep V1 and V2 at 0. So we have done that step right now. Now switch on the regulated power supply by varying V1, set VDS to some constant voltage, say 5 volt. So we need to vary this V1 and set the VDS voltage to 5 volts. So let us vary this voltage. Let us run this and let's see where it is VDS. So the VDS is 5 volt. Now stop this. So VDS is 5 volts. Next, vary V2 in steps of 0.5 volt. At each step note down the corresponding value of VGS and ID. So this has to be tabulated. Now if you look over here, VDS equals 5 volt. So your VDS is being set to what? 5 volts. Now what we need to do, we go on varying V2 and note down the values for VGS. Okay, note down the value for VGS and ID. So you need to note down the value for VGS and ID by varying the value of V2. Okay, so let us do that right now. So we will be varying in steps of 0.5 volts. Okay, so let us set this VGS as 0.5. So here we make this as 0.5 and click on OK. Now you run the circuit. So what is the voltage here? VGS is 0.5, current ID is 0. You note down those values. So VGS value is 0.5 and the current value is 0. Next, you stop the circuit, you make this as 1 volt, click on OK. Now run the circuit. So this is 1 volt, still your ID is 0. So for 1 volt again ID is 0. Next, again stop the circuit running, then make this as 1.5, click on OK. Next, again run the circuit. So 1.5, still the current value is 0, so it is 1.5, the current is still 0, so the MOSFET is not yet turned on. I will make this as 2 volts, click on OK, and then run the circuit. So 2 volts, still the current is 0, or 2 volts, still the current is 0. Stop the circuit, then make it as 2.5, click on OK, run the circuit. See, right now at 2.5 we are having 8.927 milliamps of current. Okay, you just note it down. At 2.5, at 2.5, at 2.5, at 2.5, the value of current is how much? 8.927 milliamps. Next, stop the circuit. Let's check it for 3 volts, click on OK, and now run the circuit. So for 3 volts, so now for 3 volts we just insert the table here. This is for 3 volts. So for 3 volts the value is 8.927. Next, stop this. Next, take it for 3.5, click on OK, then run the circuit. Then again the value is for 3, the value is 8.927. So stop this acceleration. Now we check the readings. At VDS equals 5 volt, you have kept VDS as 5 volt and you are providing the gate voltage. Okay, so when you provide the gate voltage, until the voltage was 2 volts, okay, until it was 2 volts, so there was no current flowing through this, so it is turned off. When you provide 2.5 volt, there is some amount of current which is flowing, so it start conducting at 2.5 volts. So you go on increasing the voltage. Okay, so if you go on increasing the voltage, so the current would be increasing. Okay, so this is regarding the transfer characteristic. So now what we need to do, you plot the graph. So this is your VGS and this is your ID. Okay, VGS versus ID. You take the VGS along the x-axis and ID along the y-axis. So for 0 it was 0, for 0.5 it is 0, so for 1 also it was 0, for 2 it started conducting. Okay, you go on increasing and this is what your graph would look like. Okay, what was the VDS which you set at the starting was VDS equals 5 volts. Okay, so for VDS equals 5 volt, this is the graph which you would be getting. Okay, similarly you plot another set of readings. Okay, so first reset the circuit again. Okay, you just reset everything. So let's make this as 0. Okay, let us make this also as 0. Click on OK and run the circuit. So everything is being reset. Now take the second set of values. Okay, second set of values means for VDS2, which is equal to 10 volts. What does it mean? You need to make this VDS as 10 volts. So we'll be making VDS as 10 volts. Now you go on varying VGS and note on the ID. Now we go on changing the value here 0.5. When you set for 0.5, you note on the value for VGS and ID. VGS and ID. Next 0.5, after 0.5, 1. You take it for 1. What is the value of ID? You take the other set of reading. Okay, so again you'll be getting the graph which is almost similar to this, but it will be having the higher conducting rate. Okay, so this is regarding the transfer characteristic. Okay, next we will be studying the now let us consider the second characteristics, that is the drain or output characteristic. So first make the connection. So the connection is being made. Initially keep V1 and V2 to 0 volts. So let us make V1 and V2 as 0 volts. Let us make this as 0 volt. Okay, next let us make this as also 0 volt. Okay, now run this. So everything is 0, so stop over here. Next, by varying V2, set VGS to some constant voltage must be more than the threshold voltage. So we'll be setting V2. So we will be setting V2 such that it should be greater than threshold voltage. So the threshold voltage means, from the earlier characteristic we came to know that the MOSFET starts conducting at 2.5 volt. So we need to set this VGS to 2.5 or above that 2.5. So let us make this as 3 volts. I will be setting this as 3 volts. Okay, so this is being set to 3 volts. We run this circuit. So this is showing 3 volts. Okay, now by gradually increasing V1, note down the corresponding value of VDS and ID. So by gradually increasing V1, okay, by increasing V1, we need to note the value of VDS and ID. And note, just observe here, what happens is MOSFET jumps into conduction state. The voltmeter which is connected across the device as VDS reads approximately 0 voltage. Further increase in voltage V1 source cannot be read by VDS. So what happens is, since the MOSFET is conducting, so this VDS will not be able to show the approximate voltage which is applied over here. Okay, so we'll be taking this V1 reading and we'll be plotting the value of ID. Okay, so that should be considered in this case. Okay, and we'll be using that values and we'll be writing the value of VDS and ID over here. Okay, at VDS in volts. Okay, let me take here. First let me make this VDS as 1 volt and run the circuit at 1 volt. So you're getting around 1.786 milliamps. Okay, so write this as at VDS equals 1 volt. So here you are not able to get the voltage is in terms of microvolt. So we'll be writing this VDS is 1 volt. ID is 1.786 milliamps. Now let's make this as 2 volts. At 2 volts, run this. So at 2 volts, so the value is 3.57 milliamps. 3.57 1 milliamp. And next I'll stop this. Let me make this as 3 volt. Okay. So here at 3 volt it is 5.375 millivolts. Next let me make this as 4 volt. At 4 volt, so at 4 volt, so it is 7.142 milliamps. Next at 5 volts, at 5 volts the value is 8.927 milliamps. So this is the voltage which should be getting. So when we provided 5 volt over here, so the VDS was reading around voltage of 412 micro volt. Okay, let 412. Okay, so next at 4 volt, if we run the circuit, so here it was 329 volts. Next at 3 volts, let me run the circuit. It is 247 micro volts. Next at 2 volt, if we run the circuit, it is 165. Just look over here, it is 165 micro volts. Next at 1 volt, it is 82 micro volts. So the value within the bracket is the voltage across VDS, and the outside the bracket value is the V1 voltage. So we need to consider the value of voltage which is present within the bracket to plot the graph. Okay, so we will be removing this 1, 2, 3, 4 and 5. Okay, so we need to plot the graph against VDS in microvolts. Okay, should be in microvolts, and ID in microamps. Okay, when you plot the graph, so this is what it looks like. Okay, when you are increasing the VDS, okay, so the current is increasing, right? The current is increasing for the value of VGS. So that is what shown over here. For VGS equals 3 volts, as the VDS is increasing, the current is increasing rapidly. Okay, so the current is increasing rapidly. So this is for one set of reading. Next, same thing, you set VGS. Okay, I set, instead of VGS equals 3 volts, you make this as 4 volts, and then go on varying this V1 from 1 to 5, and note down the value for VDS, and you'll be getting the graph. Okay, so that will be your second graph, VGS equals 4 volts. Okay, so that would be your output characteristic. Okay, so I completed two characteristics. One was the transfer characteristic, and the second one is the drain characteristic.